Once again, here are the 6 different types of behavior that we see or observe when we're building system dynamics models. And the idea, again, is that some combination of these behaviors is what we're seeing in the real data. And in this video, I'm going to do a little bit of a deeper dive into the structure that generates oscillation. And in this slide, you see the oscillation. And in this case, this was drawn pretty much by hand. And it's a dampened oscillation. And that each cycle through from peak to peak, it's getting lower and lower and lower. If you see an expanding oscillation and it continues to grow and grow and grow, I think this would indicate that there is a problem either with your formulation or the delta time that you are using. The suggestion for oscillatory systems is that you use Runge-Kutta-4 and use a small enough DT that it's appropriate. I've now pulled up a slide that's containing the Lotka-Volterra model, and don't trust me on the pronunciation of those names. And you can see here that it's a derivative, and it's AX minus BXY, and it's CXY minus DY. And if you think about this, this is simply the flows. AX is the inflow, and BXY is the outflow, and CXY is the inflow, and DY is the outflow. And we're taking the derivative of X, and taking the derivative of Y. So X happens to be the prey, and Y is going to be the predators. And the reason I know this is that the CXY is an inflow, so it's the births, and the idea is that the births, predators are eating prey, and that is where the births are coming from. On the other hand, the BXY, the Y is the predators, and the predators actually have to be part of the calculation to figure out how many prey are being eaten. And from this, we should be able to start building a simulation model that will run and generate predator-prey dynamics of oscillation. And again, these are all simplified models. If you want to follow along and build this model, you might want to print out or just capture on paper this structure along with at least one of the parameters. And I'd take the parameter on the top left-hand side where it says fractional birth rate. That's the fractional birth rate of prey, and it was initially set to 0.1. And what the students in this class had done was they had selected the number of predators and the number of prey. And they'd selected the number of predators to be 100 and the number of prey to be 1,000. And that's a 1:100 ratio, which is not unrealistic. It's probably on the upper bounds, but it is not realistic. So the idea is that we should be able to back in and build a model that is in equilibrium, and then if it's knocked out of equilibrium, like a predator-prey system, it should then begin to generate an oscillation. So we'll move on and we'll start building a model and Stella Architect of this and see if we can get this to happen. And I have Stella Architect open now, and the first thing I'm going to do is double click on the white space and open this up. And because we're dealing with predators and prey, I'm anticipating that this is going to happen over a very long time period. And for now, this may be wrong, but I'm going to select it going from time 0 to time 200. And the units, or the time units, will be years. And because I'm anticipating building an oscillatory system, I'm going to jump in initially and go to Runge-Kutta-4, and that's what I'm selecting here. And this is the DT. It's just a little bit more accurate or sophisticated way of doing the calculations when the simulation is running. So I'm going to go up, and we had X was the prey. And I'm going to click on my stock and drag it down. I'm just going to make this a little bit larger. Double click and make this prey. And I could put it in as though this was the X variable. I think I will do that. I don't like putting brackets in my variable names because it's sort of, when you're looking at equations, they'll have quotation marks around it and stuff, but that's okay. So I've got the prey, and the prey, there has to be births, right? And that was that AX. And so I'm going to call this prey births. And there's going to be prey deaths. I'm going to click on my rate variable again. I'm going to click right on top of the stock and drag it to the right. And this is going to be prey deaths. And that's okay. And I'm going to go down and bring another stock down in here. And this is going to be for my predators. And I'm just going to drag this and use all my space up. I like my stocks to be the same size. So I started with prey, so I'm going to double click on this. I'm going to come down to the bottom right where I see the paintbrush or the style settings. I'm going to click on this, and this is 106 by 83. So now I'm going to double click on this. It stays on the style sheets that I'd selected before, and I've lost track of what this was. It was 106 by 83. So I'm double clicking on this one, and it's 106 by 83. And then my stocks are going to be the same size as all. And I can do this with any of the variables in the model. So I'm going to double click on the stock one, and I am going to label this predators. I click, and I'm going to drag that into the middle. And of course, predators are going to have predator births. And this is actually the predator bursts. The formulation for that, if you go back and look at the Lotka-Volterra, should be, it was CXY. I'll put parentheses around that. I'm going to go back into the predators, and I just want to rename this, so I've clicked on the name, and I'm going to put Y in here, just so that if you go back and look at that formulation, everything will be clear. Just going to click, and I'm going to hit a return so it's square in the middle. And I'll actually do the same thing. The predator, or prey births, was actually going to be, there was a minus sign in that, but that's catching that it's an outflow from the stock, right? So I don't have to worry about that. But it was going to be BXY. And the predator bursts was simply going to be A multiplied by X in this case, which is the prey. I think whoops, I'll put that back. There we go. And I'm going to click on one more rate, and I'm going to drag this, and this is going to be the predator deaths. And I'll just square this up. I like squaring these variable names up. I think it looks a little bit neater. But it may not be happening here. I'm just going to skip at this point. And, oh, the predator deaths. If I double click or go into this name, this should simply be, oh, what did they have? I think they had DY, if I'm not mistaken. And now we have the basics for this. And the students who were there had picked that the prey, if I double click, I'm going to go to the initial value, is going to be 10,000. And I'm just going to give them a unit's name of prey. And if I go to predators and double click and open up, the initial value is going to be 100. And this will be predators with an S. And now I need to figure out the A, the B, the C, and the D, which are going to be these converter variables or auxiliary variables if you're using VenSim. And the first was, it was A, but this is the fractional birth rate of prey. And this was labeled A in that formulation. And I'm going to just click and add the other ones on. And there was B, which was going to be the fractional death rate of prey. It's going to be B one more time. And this is going to be the fractional birth rate of predators. And that was C. And the last one, I'm clicking on this converter and bringing it down. This was going to be fractional death rate of predators. And I am going to make that, that was D. And now in the formulations, we can see how these are all connected. It was A times C. I've gone up to my connector and connected that. I'm going to push the Option key down and it selects the last thing I selected in the Mac. And I will go there. And then on the outflow there, it was B times C times Y times the predators. So those three are going to there. My predators, the predator deaths, I go down this way and I can just grab and move that to the top. And then it was D times Y. And there we go. And CXY. So now it's going to be C times X times Y. And now I can go in and do the math that was there from the Lotka-Volterra equations. And this was just, it was C times X, predators, or their fractional birth rate, times the number of prey. If I click on the prey deaths, these three were multiplied by each other. And the minus there simply meant it was an outflow from the stock, right? So we've got that because it's flowing out. If I go to predator deaths, it's simply going to be predators times the fraction. And if I go to predator bursts, it was simply all multiplied by each other. So the fraction times the prey times the predators. So we're just about done. And right now, we want to start the model in equilibrium, so we got to do a little bit of guesswork. And perhaps we would actually have data on what the fractional rate of, or the annual birth rate for prey would be. And right now, in the example I gave you, and I just throw this up on the board to students so they can back into these numbers, they had picked 0.1. So I'm going to go in and say it was 10% birth rate. So this is 0.1. And this is going to be dimensionless per year. It's an annual birth rate. And so now I know if I have 10,000 and it's a 10% birth rate, simple calculation here that I know that this is going to be 1,000 is what it is. So I know in order to be in equilibrium, my inflow and my outflow have to be equal. So this has to be equal to 1,000. And I only have one unknown, and it's 10,000 times 100 times X, or this B, and that has to equal to 1,000. So I'm going to pull a spreadsheet up now, or go to my spreadsheet. And I have, this is going to be, I'll just label these. So this is going to be my prey. This will be my predators. And what I do know is the inflow for prey is going to be equal to 1,000. And now all I have to do is really solve for this. It's relatively simple algebra. So I've got the, let's see how I want to do this. I'll start with the 10,000. And then it's going to be times, and then it's going to be the 100, and then there's going to be another times in here, and then it's going to be X. At X is an unknown. Actually, I'll go back and make a B because that's what we're trying to solve for, right? And that's going to be equal to, and I know it's going to be 1,000. So if I'm multiplying these two, I can put an equal sign in there, and it's just this times 100. So I've got that value times b is equal to 1,000. So all I have to do is divide each side by this value, and I should be set with the fraction it should be here. I'm going to put an equal sign in and say it's 1,000. Divide it by, this looks like 1,000,000, and it's going to be 0.001. I'm going back, I'm going to double click on this, and this is going to be equal to 0.001. And now the units might be tricky here, because what's actually going on, this is the fractional rate at which predators eat prey per year. So the units here should be the fraction of predators per prey. Oops. Per year, right? Or the fraction. I should restate this. This is going to be, this is the predators, the fractional rate at which predators are eating prey. And the prey death has to be in units of prey per year. So this is going to be the fraction of predators per year. And now, so this part should be in equilibrium now. We'll test this in a minute, but because we have a couple of variables we have to figure out, we'll do the same thing. So now the next question should be, what is the predator deaths? How many are occurring? So I can make a guess at the fractional death rate. So let's say they lived for 10 years. So if they lived for 10 years, I can take the reciprocal of that. So I'm going to go back to my spreadsheet. And I think prey are going to live for 10 years. And doing the reciprocal, I would just divide the 10 into 1. So it's going to be equal, or 1 divided by 10, yeah. And so if they're living for 10 years, this is going to be 0.1. So I will double click on this and say they're going to live for 10 years on average, and that will be 0.1. And again, this is the fraction per year. This is dimensionless per year. Because I have it in the model already, I can go down and select that. And now, if this is 10% and I have 100, I know I'm losing 10. So now I have to figure out what the predator birth rate is, given this many prey. And so the fractional birth rate here is the unknown that I have to calculate. What I know is, again, it's the 100 times the 10,000 times the 100. And I have this unknown, and in this case, I know that it should be equal to 10. So I can go back to my spreadsheet. And so I've got the 10,000. I have that formulation right here. But instead of being equal to 1,000, it should be equal to 10. So I can just type 10 in there. And now I'm getting scientific notation. So it's 1, 2, 3, 4 zeros and a 1. So very small birth rate. 4 zeros and a 1. And the units here, this is the fraction, so it's dimensionless. And it's per prey per year. And I have one unit warning, so let's go in. It says prey deaths is incorrect. So I have predators with an S. I spelled predators incorrectly here. I'll go in, and now my units are all correct is what it is. So now we're going to see if it's going to simulate in equilibrium. I'm going to make a new graph here. I'm going to double click, plus I'm going to put, I'll put the prey in first, hit the plus sign, hit OK, and it's in. And now I'm going to add the predators. I don't want these on the same scale because there's such a difference, 100 to 10,000. So I'm going to click on the right axis, and I've just slid because I had predators selected. It's on the other axis. The other thing I know that I want to do is I'm going to make the prey go from 0 to 200. And I'm going to click up on the predator. So I'm setting the min Y value and the max Y value so that they're locked in. And I'm going to go from 0 to 20,000. So I know that it's starting out at 10,000 and 100. So I'm setting this up so that it's in the middle. I'm going to click on my wrench, and I'm going to label this Predators versus Prey. And now I am ready to simulate. I'm anticipating that this should be in equilibrium when it runs. And it is. I'll hide that for now. And now what I can do is I can knock it out of equilibrium. I can increase the birth rate of prey. And now you can see that I am getting a sustained oscillation over these 200 years. I can hit the U-turn button, put it back, simulate again, equilibrium, and then I can change the fractional birth rate of predators. I'm getting the oscillation. Just going to return. And now what happens if my death rate is different? I get the oscillation, and I'm going to do it one more time for my other constant, which is going to be the fractional. So the structure of this model generates this oscillation. So the next question is going to be is, what is that structure? What feedback loops are generating this? And one other thing I'd like to point out is these numbers do not look right. The fractional birth rate for predators seems extremely small. And this is a simplified model of the real predator-prey relationships. But I'm betting that we could get some data and back into what's really going on in this system, although it might be a little more complex. So for now, I'm going to hit and simulate. And let me just knock it out of equilibrium a little bit so that it's oscillating. I'm going to go to this triangle and open this up. And I've got the feedback loops here, and I'd like to label all of my feedback loops. I'm going to click on the flashlight, and it shows me it's highlighted the feedback loop here. So I can click on this loop label now and just come over and place it in here. So I've got the R1. I'll go down to the next. I just want one selected at a time. And so this is the B1 feedback loop, and there that is. Place it in there. And now I'll go to my third feedback loop. There's another reinforcing loop, so I've got two reinforcing loops in this system so far. I'm down to my B2 feedback loop, and there it is. Click on the label and drop that in. Now I'll go to the last one and just click on that. And there is my feedback loop that is balancing running through there. I'll click on the loop label and drop it in. And now when I simulate this, I can see how these feedback loops are bouncing back and forth. If I go back, I can see, looks like that B1 feedback loop is getting stronger and weaker. And in the interim, this B3 feedback loop is getting stronger and weaker. And this is what's generating my oscillation. And the rule of thumb is to generate an oscillation, you need two balancing feedback loops that are linked. One of the feedback loops is going to be, it'll have a first order control only, or it'll be a minor feedback loop. That's the B1. And we mean that the prey is going directly to the prey des, which is coming back to the prey. So this is a minor feedback loop. It's not running through any other stocks. And now if I go and wait and see, there we go. The B3 feedback loop is getting strong now. And this loop is running through a stock. It's going from prey to predator burst, to predators, back to prey bursts, back into the prey. So I've got this B3 feedback loop. And it's these two competing with each other that's generating this oscillation. And the B3 feedback loop running through an additional stalk creates a delay. And that's why they don't come into equilibrium, and they're always chasing each other. And that'll be it for now. So hopefully this makes sense. Feel free to ask questions. Thanks.